This lesson is entitled Rates of Change and Tangents to Curves. So in this lesson, we will begin to develop the concept of a limit. The foundation of calculus is this idea of a limit. And so in this lesson, we start to unpack what that means and how to evaluate limits. We're going to use limits to describe the way a function changes or how it varies. And so different functions vary different, they change differently. Some have small changes in x, which produce small changes in f of x. Other functions have values that jump or vary erratically, or some functions tend to increase or decrease without bound. The fact of the matter is functions change. And so you and I will be using this notion of a limit to distinguish among these behaviors, how these functions change. So let's start with a definition. Okay, so this is the definition for the average rate of change. I try to highlight and put in bold here what it is I'm defining. So the average rate of change, given any function y equal to f of x, we can calculate the average rate of change of y with respect to x over this interval x sub 1 to x sub 2. Okay, and so basically this is delta y. This is the capital Greek letter delta that we use to represent change. So this is delta y over delta x. In other words, the change in y divided by the change in x. So we have the change in y divided by the change of x, and it is equal to the change in the values of f of x sub 2. X sub 2 is that right endpoint, right? F of x sub 2 minus f of x sub 1. Okay, so this is the change in y divided by this length here, delta x, which is the change between x sub 2 and x sub 1. Okay, now I'm going to show us a picture in just a minute to help us understand this definition. What we can also do is we can write this equivalently by writing f of x sub 1 plus h minus f of x over h. Actually, this is supposed to be x sub 1. Let me change that. Make sure you change that in your notes. X sub 1 there you go. So f of x sub 1 plus h minus f of x sub 1 over h. And this h here can represent this length here between x sub 2 and x sub 1. So I'm going to show you a picture and how h can be used to represent this length x sub 2 minus x sub 1. So geometrically, this rate of change of our function f, here I've drawn a function f here. It's this curve. And geometrically, the rate of change of our function f over this interval between x sub 1 and x sub 2 is the slope of this line that's going through our curve in 2 points, point P and point Q. Now, a line joining 2 points on a curve like this is called a secant line. So therefore, the average rate of change of our function f from x sub 1 to x sub 2 is the slope of this secant line. We can call it the slope of the secant line PQ. Okay. Now this is really important. Let me update my picture, because what I want to show you is this distance here from x sub 1 to x sub 2. I'm going to draw that out for you. That is what we're calling h, or delta x. And then this distance here, this vertical distance, is what we're going to call delta y. Let me label my picture as such. So here we have it. So this distance here between x sub 1 and x sub 2, we call it the change in x, right? Delta x. And we can call that change, that length, we can call it h. This is delta y, which is the change in your y values, right? The change of y. All right, so again, the average rate of change of our function f from x sub 1 to x sub 2 is the slope of this secant line here. Now, this is really what's important. As point Q approaches point P. So imagine point Q getting closer and closer and closer to point P along the curve, then this length right here, this distance, which we can call H, right? The length of H of this interval over which this change occurs approaches 0. So imagine Q is here, then this distance here has decreased, right? Imagine Q is here. Now the interval is even smaller. Imagine Q is here. The interval, look how small the interval is going to be there. And imagine as Q gets, infinitely close to P, the interval here gets really small. In other words, the length H is approaching 0, right, as point Q moves along the curve and gets closer to point P. We will see that this procedure, letting Q get closer and closer to P and calculating the slopes of these secant lines as point Q gets closer to point P, this procedure leads to the definition of the slope of a curve at a point. Okay, so it's all leading us to that big definition. So at this point, this is the average rate of change. It is the distance. Let me see if I can scroll back up here for you. Yep, I can't. Oh, I think I can. Hold on. There we go. So it is the difference between these function values over or divided by the difference of these x values. Basically, the change in y divided by the change in x, which is essentially the slope of this secant line. All right, great. I'm going to show you another picture here just to really drive home the point here. So this is a function, okay, and I have 2 points, P and Q, and I'm letting the point Q travel along this curve and get closer and closer to point P. And my point is I really want to illustrate geometrically this idea that these the secant lines here, as point Q gets closer to point P, the secant lines actually approach something called the tangent line. So let me see if I can illustrate that for you. So here is my first secant line through these 2 points, and imagine now Q is over here somewhere. It's moving closer to point P. Then my secant line would be something like this, right? And imagine Q moves now even closer to point P. Then, this is going to get sloppy here, but I think you're going to see the idea. And now here's my secant line here, right? And so we're allowing point Q to get closer and closer and closer to point P. So now here's my secant line, and it's all leading up to, as point Q gets closer and closer to point P, the secant line ends up approaching something called, I wanted to do a different color for you, something called the tangent line. The tangent line is the line, I can do better than that, hold on. The tangent line, there, that's better. The tangent line is the line that touches the curve at one point, whereas a secant line is going through the curve at 2 points. The tangent line just grazes the curve, just touches it at one point at point P. So as point Q gets closer and closer and closer to P from either side, okay, I could have drawn this picture where point Q is over here and it's approaching P from this direction. Either way, as point Q approaches point P, these secant lines, right, are becoming the tangent line. Now, what's really important to note is we're going to say that the tangent line right here, this tangent line to the curve at point P, it's a line whose slope is the limit of the secant line slopes. So the limit of all of these slopes, the limit of the slopes of these secant lines as Q approaches P. All right, very good. Now keep in mind, we will formally define or clarify this limit idea in a further lesson, in an additional lesson. All right, very good. Let's look at an example, shall we? Okay, folks, look at this example. Find the slope of the tangent line to the parabola y equals x squared at the point 2, 4 by analyzing the slopes of secant lines through 2, 4, through that point, through 2, 4. Write an equation for the tangent line to the parabola at this point. So there's two things we need to do. We first need to find the slope. Once we find the slope of the tangent line, then we can write an equation for that tangent line. So it's two parts, okay, folks? Finding the slope of the tangent line, and we will do that by analyzing the slopes of the secant lines, okay? Once we have that slope, then we can write the equation for the tangent line to the parabola at this point 2, 4. All right? Okay, we're going to use the definition for the average rate of change, right? So we wrote this down a minute ago. So the secant line slope is delta y over delta x. Remember, this means the change in y divided by the change in x. And we're going to write it this way. So we have f of x plus h minus f of x all over h. Now, in the definition that we wrote down earlier, this had a subscript x sub 1 and then x sub 1. I don't need a subscript here because I don't have different x coordinates that I need to differentiate between. So this x value here is given, it's 2. Okay, that's your x coordinate. So then this is equivalent to being f of 2 plus h minus f of 2 all over h. Okay, I think I need to move this up a little bit so I can expand this. So this is equal to, now remember that your function f is simply x squared. So your function squares whatever you are plugging in, right? It squares your input. And this notation says 2 plus h is your input. So then this is 2 plus h, quantity squared, minus 2 squared all over h. So let's simplify this. So then this is 4. Expanding this binomial here is 4 plus 4h plus h squared minus 4 all over h. Now, this 4 here is the opposite of negative 4. So those cancel. And I think I need to move up again, folks. Sorry about that. So this is equal to, you see how the two remaining terms in the numerator both have h, a common factor of h. So I'm going to factor out that common factor of h, which leaves me with 4 plus h all over h. And these h terms cancel, and you're left with 4 plus h, or h plus 4. All right? Now remember, we must remember our conversation earlier about this value h. Remember, the value of h is the length of that interval between your 2 points on the curve. And so remember what we were talking about earlier, letting h get smaller and smaller and smaller. Remember, we said h is actually approaching 0. Which means the slope then, we take the slope to be 4. 4 to be the parabola slope is the parabola slope at this point that they gave you, which is, let me scroll back up so we can see. There it is. So then we're saying the parabola has slope 4 at this point 2, 4. Now that we know what our slope is, I forgot to write this down. So this is equal to 4, right? This is our slope. This is the slope of the parabola. The tangent line has slope 4 at that point, 4, 2. The tangent line to our parabola at the point 2, 4 I think I said 4, 2. I think the point is 2, 4. The tangent line to the curve at the point 2, 4 has slope 4. Now we need to write the equation for this tangent line. You can use the point slope form for an equation to do this. So then it is y minus, now y sub 1 right here represents the y coordinate of your point. They gave you 4, right? I'm talking about this point. Let me see if I can scroll back up. I don't mean to make you dizzy here, but this is your x sub 1 and y sub 1, right? So that's why I said, that's why I plugged in 4 right now. It doesn't have to do with that slope that we found. It has to do with this coordinate, okay? So I'm going to plug in this y coordinate and this x coordinate into this point slope form. All right, so let me go back. We're right here. Is equal to, we found the slope to be 4, x minus 2. Okay, so now just maybe isolate x, isolate y. So we get 4x minus 8 plus 4. So the equation for the tangent line, at the point 2, 4 is y equal to 4x minus 4. Because a lot of us are visual learners, let's draw a quick little sketch of what we did. So this is just a rough sketch. This is our curve y equal to x squared, our parabola, and that function was given, and so was this point 2, 4. And so what you and I did was we use the definition for the average rate of change to calculate the slopes of secant lines. And what we did is we let h go to 0, and we found that the slope of the tangent line at 0.24 is 4. We also found that the equation for this tangent line is 4x minus 4. Okay, so that's really important that you and I are using the slopes of secant lines to find the slope of the tangent line.